So first, I would like to thank Professor Toshiyuki Ogawa and all the organizers for the invitation and wonderful organizations. So in this talk, I'm going to focus on Lotka-Volterra competition system. So first, let me mention some motivation of this study. So an important issue in ecology is biodiversity or coexistence of many species. So in an article by Milkevich, it is mentioned that the estimated numbers of current species on Earth are as follows. For animal species, there are about 7.8 million. And for example, for the fungi species, there are about 600,000 species. So these numbers are very huge. So of course, it is a difficult problem to understand why these numbers are so huge. But anyway, important thing is to understand the interactions between individual organisms. So among others, two mechanisms are often mentioned, which are competition and cooperation. And for cooperation, it is easy to understand that cooperations should help coexistence. Then how about competition? So in this talk, we focus on competition and assume that there is no direct cooperation between species or between individuals. So there are several natural questions. Say, does competition always reduce the chance of coexistence? Or sometimes it helps coexistence? Or can species coexist under strong competition? This is also a natural question. So in this talk, we are going to focus on the Lotka-Volterra system. We know much more about the two species competition system, but less about the three species systems. Therefore, we are curious what new phenomena can be observed in the three species system. So let me make one remark. Mathematically, the two-species system is a monotone system. However, the three-species system is not a monotone system, and it has no comparison principle in general. So this makes the phenomena in the three-species system much more complicated. So let's start from two-species system. So here is the two-species Lotka-Volterra competition system with diffusion. So we have D1, D2. So they are the diffusion coefficients, and we have several coefficients here. So R1, R2 are the growth rates, and we have the interspecies and the interspecies competition coefficient here. So the negative side here means these two species, U and V, are in competition. So to understand the PD, we need to understand OD first. So I think most of us have learned this in a basic OD class about this OD system. So there are four typical situations for this OD system. two of them are the strong competition case and the weak competition case. So let me show two pictures of these two cases. So this is a phase plan of U and V. So this is U and this is V. And for the weak competition case, there is only one stable equilibrium in the positive region. So if the initial data is, say, located at here, then after some time, the trajectory will approach this equilibrium F. If the starting point is at here, then the trajectory will go like this. This is for the weak competing case. And for the strong competing case, the equilibrium here is no longer be stable. So it's become unstable. On the other hand, there are two more equilibrium become stable. That is the F1 here and F2 here. So if we start from here, then finally it will go to F1. So that means only the species U survives and the species V vanishes. So if we start from here and then we go to here and only species V survives. So this means for most initial data, only one species can survive. So this is a typical situation for the strong competition case in the ODE. So what about the PDE? So now we consider the strong competing case for the PDE. So there is a very interesting result mentioned in the Professor Morita's talk that is given by Kishimoto and Weinberg that says if the domain is convex and we consider non-boundary condition problem, then a stable steady state must be constant. So in our case, this constant must be either F2 or F1. So that means only one species can survive. So therefore, on a convex domain, the phenomenon is quite trivial. It's not so interesting. On the other hand, if the domain is far away from a convex domain, then there is very interesting results by Matano and Mimura. It states that if the domain is a dumbbell shape like, then there exists a non-constant stable solutions if the dumbbell neck is narrow enough. So these are two kind of different theorems. So how about the general situation? General situation is quite complicated, but the numeric tells us that in most situations, only one species can survive. That means if you don't allow the domain to have some dumbbell neck structures, then usually only one species can survive. So I take one example, numerical example from Mimura and Thomas' work here. Say this is initial value. These two species survive on a rectangle domain. And at the beginning, one species have high density on the gray region, and the other species have high density on the light region. Then after some time, only one species can survive. So the conclusion is that at least combine the numerical results, we know that it is very hard to see coexistence under strong competition for the two-species system. Also, I would like to remark that another result by Kishimoto said that if one considers three species problem on a 1D domain, then it is possible to find a stable, non-constant steady state. So these results indicate that to find more interest patterns, it is a good idea to look at the three-species system. So here is our three-species parabolic system. Again, we have diffusion here, and we have a lot of positive coefficients in the reaction terms. So since the system is so complicated, so we started from the study of traveling waves. So as we know that traveling waves on R1 is very fundamental to dynamic behavior of the system. So for the two-species case, a typical profile for a traveling wave is look like this. So we have a red species and a blue species. So this is a typical situation for the strong competition case. So we suppose that the profile moves to the left. So this kind of wave helps us to understand the dynamic behavior of the two-species system a lot. Also, there's one more important thing that actually the sign of the wave speed also tells us which species is stronger. So in this case, since on any bounded domain, the blue species will finally occupy all the area. So we can say that in this case, blue one is stronger. So the sign of the wave speed gives us a lot of information. And thanks to the works by Gardner, Coley, Gardner, and Kang-on, so we know that if we suppose that U and V are in strong competition, then up to a translation, there is a unique monotone wave connecting the two steady state. So the two steady state is just the one in the picture, that is F2 and F1. So this theorem tells us that there is a unique monotone wave connecting these two equilibrium, and moreover, this wave is stable. So this is for the strong competition case. So this is a very nice result, clear and very strong. Now, so how about the three-species traveling waves? So first, it is easy to construct a monotone wave like this. And in 1997, Milner constructed a wave like this. So we have a different profile for the third species. Then later, Ikeda used the wave constructed by Miller to further obtain a complicated plots like this. So these are very nice results. But however, if we try to guess what else do we have, and try to draw some candidate profile for the traveling wave, then one is easy to come out. It looks like this. Say we have a decreasing profile for V and the increasing profile for U. And then we have paths like W in the middle. So this is a very natural profile we can guess. And in what situation can we get this profile? So one possibility is from the following scenario. So we assume that V is stronger than W. So I use this notation in not rigorous way. Just a roughly way. So we assume that V is stronger than W, W is stronger than U, and U is stronger than V. Then initially, we assume that V, W, and U occupy the left, the middle, and the right region. In the long run, can the three species develop into a wave with W in the middle? If there is such possibility, then we have the opportunity to see a wave like this. So to study this three-species wave, we use some standard ansatz first. So again, this is our parabolic system. Then we let S to be the wave speed and consider the new variable Z equals X minus ST. And we consider a solution of the form UVX of X minus ST. We put this form into the parabolic system and obtain this ODE system on R1. So again, here S is the wave speed. So some other numeric results indicate that there seems no such wave. So maybe the reason we didn't see them at that time is due to taking wrong parameters I and Cij in the system. But since there are less tools for the three-speed system, therefore we decide to try to construct the training wave by explicit formulas. So let's call this type of wave type 4, since in this slide we already have 3 typical waves, so we call this type 4 wave tentatively. So go to the method by explicit formula. So we were very lucky. We could find some example of exact solutions. So this is a joint work with Li Changhong, Mimura, and Uyama, and also later with Tomac. So here is one example. So if we let the diffusion coefficient to be 1 and choose the interaction coefficient carefully like this, then we can show that this system has a traveling wave like this. Actually, the components can be represented by hyperbolic tangents. And the speed in this case is 11/15. And it is easy to check that the profile of this component is just like the type 4 profile. So this is very nice. And during the calculation, we found some algebraic relation. So if this relation are satisfied, then there exists an exact trailing wave. And the set of such coefficients form a two-dimensional manifold. Also, we can find some numerical waves. So use the auto numerical method. We can draw a bifurcation diagram. Say we take one coefficient as a parameter, say C23 here, and this denotes the wave speed S, and this point is denotes the exact solution. Then from this exact solution, we can produce the programmed by auto. So say if we look at this exact solution and fix the coefficient here, then we can find another numerical wave. It looks, say, maybe like this. So in that situation, we'll see exact solution looks like here. We have a W small here, and this is, say, U, and this is V, and the small w in the middle. And at another point here, we will see another three-space wave. In that wave, the profile of W may be bigger, like this, and again, U and V. Also, in another branch, say about here, maybe we will see a two-space wave like this. So this is a typical situation. And before go to more result about the type 4 waves, I would like to say something about the application of type 4 waves. So the first is about the spiral wave. So it is observed, the spiral waves are observed in many reaction diffusion systems, say like Fitzhugh-Nagumo systems. But for the computing system, less about spiral waves were studied. So in the 1999 paper by A, Kota, and Mimura, they construct numerically symmetrical spiral waves. So that's very nice. And the next question is that, does there exist non-symmetric spiral wave? So Mimura and Toma in 15 use a very clever idea. So they use type 4 waves. So here is their idea. Say our domain is a rectangle like this. And first, they choose suitable parameters in the three-space system so that there is a two-space UV wave like this. So this is a one-dimensional Turing wave with a speed like this. So this wave go to the right. And also, this system has a three-space wave like this. So this is a type 4, basically a type 4 wave. And the profile go to the left. And they choose the parameter carefully so that the speeds of these two waves are almost the same. The signs are different, but the absolute value of the speed are almost the same. So this, that is their conditions. Then they prepare their initial data like this. So on the left part, they put more population of species U. And on this gray part, this is a high density region for species V. And on the very thin dark region, this is a high density region for the species W. So this is their initial data. So then intuitively, after some time, in this region, these two species can form a two-space wave. The profile looks like this. And on this region, these three species can form a three-space wave like this. And the wave here go to the left, and the wave here go to the right. So they can produce a twist mechanism in the dynamics. So in the long run, they'll have a good chance to see the spiral wave. So moreover, since they choose the speed, the speeds carefully, since these two speeds are about the same, but with different direction. So this twisted mechanism keeps a very nice balance. So let me show you more simulation. So I'm sorry that this initial picture is different from this one, but the situation is similar. So at some time, you will see that two species train wave form a local wave is formed in this region. Then a three-species wave is formed in this region. Then these waves keep going and keep going, and finally we will see a very perfect spiral. So their results show that actually one can construct a spiral wave in non-symmetrical situation also. So this is good news. And moreover, in some first paper, so I would also like to mention for the spiral wave, there's also some work done by Terracini and her collaborator and others, but their result only most of them are numerical result for the spiral profile. Yeah. So in two papers by Mimura Toma and Contento Mimura Tom, they further explored the patterns formed by the three-species systems. So here is one typical example. So this is the initial condition. We have three species here: light region, a gray region, and the dark region. Then after some time, you will see the picture becomes more and more complicated. And one interesting phenomenon is that it seems that this dynamical profile seems can continue for forever, at least for a very long time. So this means all the three species can coexist together, even this is not a steady state. And also they find a very interesting new wave, like say wedge-shaped Chiun wave. So they prepare their initial data like this. We have the say U species here, V species here, and the W species on a very narrow strip. Then the profile of this shape will not change. It just move to the left upper corner. And this line indicates the trajectory of the tip. So this is a kind of a new Chiun wave. So from this result, we have some observations. So the first is that three species have more chance than two species to coexist. It seems coexistence is easier to happen as a dynamic pattern rather than a steady state in many situations. So as we can see in the spiral wave or in this picture, in these two pictures, although the pattern is not steady, but the three species do coexist. And for a three-species system, it may produce the so-called cyclic dominance. The cyclic dominance mechanism can increase the chance of coexistence. And also we found that type 4 waves actually serve as a basic type of building block for many complicated patterns. So even in this, even in this picture, we can see a lot of local type 4 wave. So therefore, these observations give us more motivations to study the type 4 wave. So our next question is how to construct more type 4 waves. So here I'm going to provide 3
maybe
is the exact solution method. Sorry.
Chiun-Chuan, maybe
Yes.
little bit problem. So could you say maybe again, maybe for a few sentences again? You stopped again.
So you mean there is some
we can't hear a few sentences.
internet problem?
Eric, do you understand what's happening?
Yeah, it seems like he's having some slow internet issues.
So how about this slide?
Can you hear us okay?
Yeah.
Yes.
Okay, good. Let's start, Chiun-Chuan. Sorry.
Okay. So let me quickly recall the observation in this page. So the first is that it seems easier to find a coexistence for 3 species than for 2 species. And one important observation is that it seems coexistence is easier to happen as a dynamical pattern rather than a steady state in many situations for the 3 species system. So therefore, when we consider the coexistence problem, maybe we should not look for steady state pattern. We should pay more attention for dynamical patterns. So like the spiral wave or like the profile here. So say for in this picture, all the 3 species can coexist, even this is not a steady state patterns. And another important observation is that one important mechanism for the coexistence maybe is the cyclic dominance mechanism. And finally, we would like to point out that the type 4 waves can serve as basic building blocks for many complicated patterns. So then let's go to the problem, how to construct more type 4 wave. So we are going to consider 3 approaches. The first one is the exact solution method. So for the 2 species system, there are some nice systematic method developed by Lotka and Numerical to construct exact traveling waves. However, for the 3 species system, since it is too complicated, so it is very hard to apply the 2 species method. So in our situation, actually our idea is very naive and primitive. So we just assume that the components of the train wave have the form of polynomials of hyperbolic tangent with degree 2. Then we plug in this form into the system and try to solve the algebraic equation. And actually, it is quite funny that the first example, I have shown to you, was obtained by hand calculation. But then later we found that it is easy to find a more exact terminal solution by Mathematica. So this is basically the method of exact solution. We have no any very nice ideas. So the next approach is weak interaction. We consider a weak interaction model. So the idea is like this. So again, this is our system for the three-speed train wave. So after scaling, we may assume that we have a coefficient 1, 1, 1, 1 here. So this standard procedures. Now, the key point is that we put a small coefficient epsilon 1 and epsilon here, epsilon 2 here. So this means the effect of W on the first two species is very small. So the first two species is almost decoupled from the third equation. So this gives us a big advantage. So this is joint work with Zhang Juexin, Li Chuanhong, Mimura, and Ogawa. So this Ogawa is our chairman, Tosh. So this is one example. So if we give some conditions on the coefficients in the system, then we can show that if epsilon 1 and epsilon 2 are small, then there exists a stable type 4 waves. And the idea of the proof is that first we consider the extreme case that epsilon 1 and epsilon 2 all are 0. So in this case, the system decoupled into two parts, the UV system and the W system. Then we can solve the existing problem. Then we use a perturbation argument. So as a corollary of our result, let me show you another result. So we let capital lambda be the set, the set constituted by all of the coefficients for which there exists a type 4 traveling waves. So we would like to know that which set of coefficients can produce type 4 wave. So we collect all of this kind, all of these points of coefficients and call it capital lambda. And here is our assumption. So the first assumption just says that the first two species U and V are in strong competition. And the next assumption is that the competition between the first two are very strong, or at least semi-strong. So what is the meaning of very strong or semi-strong? So let's go to the equation again. So for the first two equations, the coefficient C1, 2 means that the effect of V on U. So if C1, 2 is very large, then the effect of V on U is very large. And the coefficient C21 plays the similar roles. So in our theorem, we assume either this C12 is very large or this C21 is very large. So this is a condition B. So we give a low bound estimate for the largeness of the coefficient. So we have the low bound B0 and C0 for these two coefficients. And B0 and C0 is a little bit complicated. So if this condition is also satisfied, then this the theorem tells that we can choose the coefficients in the third equation suitably such that the system has a type 4 wave. So we fix the coefficients in the first two equations such that they satisfy the condition B and the condition B. Then under these assumptions, we have some freedom to choose the coefficients in the third equation so that the system have a type 4 waves if the coefficient epsilon 1 and epsilon 2 are small. So this is the content of this theorem. So apply this theorem, we get a more constructive way to show that the set of lambda is actually has dimension 11. That means the full dimension of the coefficients. So let me see how much time do I have. Okay, I don't have much time. So let me just quickly mention that there are several considerations. So in our consideration, we put epsilon 1 and epsilon 2 here. Another approach considered by A. Ikeda, Mimo, and Tosh is to consider this parameter R3, the growth rate of W. So first, we start from R3 equals 0, then of course there is no three-species wave. Then gradually we vary the value of R3 and to see the bifurcation behavior of the wave and try to construct the three-species wave in this approach. And using this approach, they can get very nice result. Then next, let's go to the third, our third approach to find the type 4 wave. So say if we consider a spatial type 4 wave with this kind of profile, that means we have a very long W part in the middle. So this may indicate that the interaction of this part and the interaction of this part are very weak. So therefore, we can break this train wave into two parts, the left part and the right part. So for the left part, the blue species is almost 0. And on the right part, the red species is almost 0. So we can consider consider it as a two-species wave. And this part can be approximated by a red-green two-species wave. So therefore, the idea of the growing bifurcation theorem is that, say, at the beginning, if we have two simpler waves like this, so can we glue them together to form a new wave? So this is the idea. And actually, there is a nice theory developed by Kokobu and the group Chilton, Terman, and Fielder to construct, to glue in waves to form new waves. So again, this is our system. So to talk about the details, so let me collect all the coefficients here, and also we put S here and denote them by a parameter mu. So this is our parameter. Now let O1, O2, O3 be the three equilibrium at this part, and this part. So for the left wave, it approached to equilibrium O1 and O2, and for the green blue wave, it approached to the equilibrium O2 and O3. And we should note that in between these two waves approach to the same equilibrium. Then the idea is that if we perturb the parameter mu a little bit to a new parameter mu hat, then maybe we can group the wave together to form a new Turing wave. And it connects to two new equilibrium, O1 hat and O3 hat. So the starting point is the existence of a O1, O2 orbit, that is this red-green wave, and the O2, O3 orbit, that is the green-blue wave here. And the goal is to perturb the parameter mu suitably to get a new O1 hat, O3 hat orbit, which corresponds to a type 4 wave. So this is the main idea. So to simplify the notation, let me use H1 and H2 to denote the O1, O2 wave and the O2, O3 wave, respectively. Then the theory developed by Kokopu and the group of Chiun-Chuan Chen. So they need several complicated conditions to guarantee the green method works. So the first is the existence of the H1 and H2 at the same time. So this is a reasonable assumption. Then this is quite complicated. So at each equilibrium, we need to consider the characteristic root of the linearized system. So let me denote them by eta, rho, nu, and the kappa, and put in some nice orders. And the condition H1 just says that the given two orbit H1 and 2 must approach to the equilibrium along a very nice direction. That means along nu or low direction. Since nu and low are the main dominance direction, so that means that our preset orbits must have a very nice asymptotic behavior. And the next, yes.
You have 1 minute left, so.
Okay, so in that case, let me skip their condition and several transversal conditions. So going back to our situation, so suppose our preformed wave looks like H1 and H2 look like this. So this two-species wave, this also a two-species wave. And first, we need to assume that strong competition for the three species. Then we need to show the existence of these two waves with the same wave speed. So this is a difficult part. And we need to assume that these two species waves are stable as the three species as a series wave in the three-speed system. Also, we need some condition on the characteristic look of the linearized system. So say we need that the behavior of H1 and H2 is dominated by the component V and W near O1. And also we have similar condition for O2 and O3. So under these conditions, so first let me denote our parameters by tau. Then this is a joint work with Chiun-Chuan Chen. He's also in the audience. Assume that we have A1 to A4. Assume that this condition hold for some tau node. Then in a small neighborhood of tau node, there exists infinitely many taus for which the Lotka-Volterra system has a type 4 wave. So these taus are suitable perturbation of tau. So by this method, we can construct more type 4 wave. So let me show you one example. So again, this is our OD system. So, and we assume that the coefficients satisfy this condition. And again, two coefficients are very large. Then we can show that this system has a type 4 wave if we perturb tau suitably. So, and also we have some necessary condition, but let me just skip it. So finally, let me quickly make a summary. So it seems a dynamic pattern are easier to be observed than a steady state in many situations for the three species. And the type 4 wave serve as a basic type of building blocks for complicated patterns. And we have found several methods to construct such waves. And also we have many questions. So how to find more of this wave, and how to construct spider waves analytically, and how about, say, for the 4-speed system, and so on. So let me stop here. So thank you very much.